Okay, cool. Yeah, thank you for holding out. I mean, being here in the middle of lunchtime for probably, it's going to be a fairly technical talk, but I'm happy to see you all. I'm from a company called Modulai. We're a machine learning agency. We help companies with end-to-end machine learning projects, taking full responsibility of defining the business problem in terms of machine learning and actually delivering the full solution deployed and that can create value when the project is finished. It's really cool. But I'm not here to sell. I'm here to talk about something super exciting that is going on right now in machine learning. And I realized that I didn't sell my title that well as well, but feature attributions, that's the technical term for explainability or explaining machine learning models. So it's a special way of explaining your neural network, for example. And one type of neural network that I'm interested in, that's very applicable to many real-life business problems, is sequence labeling neural networks. And that's a more technical term for a time series of events. And in particularly, we are looking for using that in finance, in financial technology companies or for banks. So the application that I'm going to talk about today is basically how we use it in credit risk, for example. Trying to make sense of these more complex models that show up when building neural networks. So, general introduction to the problem and the axioms of local attribution methods. I will come to that, what exactly that means. And then the application to finance, and then in the end, the use case where we actually apply this in some made-up data we have. Okay, so when we talk about machine learning, we often say it's a black box model. But what do we actually mean with the black box model? So the definition of the black box model is that it's completely hidden to us. But that's not true for machine learning models. We know exactly how they work. And when you do black box for testing, for example, you can only analyze the y's that comes out when you put in x. And that's definitely not true for neural networks, for example, because we have every weight, we have every connection. It's not a black box model, so I stop using that word. The issue is one of complexity. So we can say that actually it's more complex that we cannot understand by just looking at the model. But we can still understand it. It's still there to be analyzed. So what is explainability? And I took this definition from Wikipedia. Maybe I should read here, it's easier. Explainable AI refers to methods and techniques in the application of artificial intelligence technology such that the result of the solution can be understood by human experts. So that's just the top of the Wikipedia page on explainable AI. But what we actually mean with understood, I mean, it's a highly ill-defined concept. So it's more of a philosophical question. It's the topic of epistemology, actually. And we need to quantify this statement to actually make sense of it in a more data science or science context. I mean, I can claim that I understand my cat, I can claim that I understand my girlfriend, but there is no way of actually quantifying that is true. So we need a better way of actually saying what is explainability. And that is when these axioms and the local attribution methods come in. So attribution is a quantification of explainability. So f is my machine learning model. Y equals to f of x is how it works. I put in something x, that could be tabular data, it's an image, it's a text, it could be whatever I want, and y is the prediction. So having my model f, I can define an attribution function that is dependent on my model f, that for every input I take will give you some attribution, a. And a is of the same dimension of x. So maybe you have seen these saliency maps, for example. That's exactly this, that you feed in an image and you get out these colors, the red intensities. That's the A matrix here, if x is a matrix. And the components AI tell us how much the variable xi actually contributed to the output. A positive value of AI means that it had a positive contribution to y. A negative value means that it had a negative contribution to y. So again, if I do object detection, I mean, if I have a cat, but it's actually wearing a hat, maybe the hat will be indicated at reducing the probability of being a cat, while the whiskers will increase the probability of it being a cat. So what we're after is actually finding this function A, because we cannot just put in any function A here, because we don't, in that way we cannot really trust the outputs. So, right, that's where we go to these axioms. But before I go into axioms, I want to say why is it important to actually quantify this? So, in credit scoring, which is a field I have been working with a lot, actually you have legal requirements on explaining the model. So this is in the US. A consumer must be told if information in a credit report has had an adverse impact on him or her. That's the Fair Credit Reporting Act in the USA. Scores are subject to prohibitions against discrimination under the Equal Credit Opportunity Act. So this means that legally, in the US, you need to supply the 4 key factors for rejecting an application that should be reported to the customer. Let's say I apply for a loan and I get rejected. I need to know the 4 top factors. And this requires us to actually understand the machine learning model that has given the suggestion to reject this customer. And that's exactly given by these attribution functions, AF. I rank the A's, and I top 4 negative ones. And I send those to the customer. I am obliged by law to do this in the US. In Sweden, the legislation is less strict, but we have similar practice, right? So, oh no, I mean, this is hard, doing it in a good scientific way. So how can we convince the financial authorities that our attributions are correct? That's the big question we need to answer. And I'm in the financial context now, but this applies as well to stakeholders or the business owners of the company. Maybe the CIO wants to know why this machine learning model exactly did the predictions that it did, because it affects the portfolio of assets in some very important way, whatever. You need to know that the attributions, and I cannot just claim that I understand my model as a human expert. I mean, we need to quantify this. So that's why we need axioms. And now here comes the mouthful. But actually what you do is that you put down restrictions on this function f that you can argue are reasonable from the application that you have. And these axioms have been recently appeared in machine learning literature. I don't know if you have seen the Shapley package that can explain XGBoost predictions, or the Facebook released Captum just last week, I think, where they have these attribution methods that build on these axioms. So we'll just quickly go through them to get a sense of if they make sense or not. So efficiency, that means that all my A's should sum up to the probability of actually being a cat. And that makes sense because we want to know, let's say I make a prediction that this image is a cat by 30%. I could say that 15% is because of the whiskers, 5% is because of it has 4 legs, then maybe 10% is because of it has the shape of a regular animal, a mammal, let's say. And it should add up to these 30%. That's one of the things we want. We also want linearity, for example, that if I have 2 models and I add up the predictions of those, the attributions should also add up. And that also makes sense because let's say I have a gradient boosting. My prediction is actually the weighted sum of all my weak learners. So in that sense, actually, the final attribution is just the sum of the attributions for all these weak learners. So it's a consistency check of actually how are my attributions, are they making sense? Ensemble models is another example. Dummy, let's say I have a feature that is not used at all by the model. Then I want the attributions to that feature to be 0. And this is actually not as trivial as it sounds, because if I want to be true to my data, I can have a variable that is not in my model, but is highly correlated with my features that are in the model. So if I start tweaking that variable, I will actually change the output of my model if I take care of the correlations. So there are many methods out there that actually break this one, because they stay true to the data. So some more ones. Symmetry. Let's say I have 2 features that are used in exactly the same way by my model, then the attributions for those features should be the same. I have the income in SEK, and I have my income in euros in the model. They should, by up to scale, be given the same attributions. Monotonicity is I have two models that one are consistently more dependent on one variable than the other, then the attributions for that in that model should be higher for that feature. We also have scale invariance. Say if I have a credit risk model and I want to measure the risk in terms of the income again in SEK, that should be the same as measuring in euros. So this is scale invariance is just that you can do some affine transformation of features, and that's changing currencies in affine transformation. You could also be temperature going from Celsius to Fahrenheit. That's also an affine transformation. So we can just agree that maybe these ones make sense, right? Especially when we do credit risk, for example, because we can argue that the axioms that we use should be consistent and sort of make the attributions more reasonable, easier to understand. So what happens if we do this? Then we can actually go back to math from the 50s, 70s, and 60s, and realize that people have been doing exactly these things, but for cost allocation in economy, so that you want to attribute costs to participants in a market, for example, if you have some idea that the cost should be distributed fairly among the actors in the market, for example. And you end up with something, oh, this is a big slide, but let's start somewhere. You end up with something called Shapley values from a game theorist in the 50s that actually introduced these attribution methods in game theory. And the last 10 years, basically, people have been applying these methods on machine learning. So we have a couple of different ones out there: Shapley values, Shapley-Ullmann, Shapley-Shubik, conditional expectation Shapley, that are axiomatic. And what we mean with axiomatic is that if you start with these axioms, you can derive that these methods are the unique ones that give you attribution functions that satisfy these axioms. So that's why we want this, because then we can actually go back to the financial authority and say that, okay, here's my attributions, I use these axioms, all of them make sense, I can use these uniqueness theorems from game theory, and I end up with this formula for my attributions, and hence I comply with the legal requirements. That's the argument here. And this is an area very much of active research. For example, in August, when I first hold this talk, Google just released a paper where they discuss all these different axioms that you have and what kind of attribution methods you get out of them for when you try to explain your neural networks. And as they claim in this paper, it's very much not settled exactly which axioms you should use and what attribution methods you end up with. So, for example, in the Facebook package they released last week, they have a couple of different ones. Some of them axiomatic and some of them not. But I think that in the next couple of years, we will have more ideas exactly which one of these are the right ones. So, read this paper, it's really good. Also, let me see here. Yeah, this one. This is a paper by, I think you recognize one of the guys here, Goodfellow, for example, from GAN fame. He actually goes through a lot of these attribution methods in this paper. It's also from this year, I think, with application to object detection. How am I doing on time? Oh, shit. Not good. So, where they actually claim that these Shapley methods don't make sense when you're trying to debug your network. So they go through the method that these guys introduced in this paper, or their previous paper, and claim that it's not good for debugging your network. So there's actually no consensus if you should use these axiomatic methods or not. But their application is different. They want to debug their object detection networks, while we, for example, want to comply with the legal requirements of financial authorities, which is a different context. So it's not obvious that probably both of them can be true. But in this paper, they claim that there are issues with these axiomatic methods. When did I start? Nobody knows. 125. 12 and 25. Okay, so I've been doing 15 minutes. Good. Then the time on this one is wrong. Good. 10 more minutes. So in this case, in the logistic regression case, that's the standard method that we used back in the day when we didn't have gradient boosting or neural networks, more commonly used, let's say. And in this case, attributions are simple. We just take the weights and multiply them with the variable that we put in, and maybe we subtract some number. This could be, for example, expectation values of your features over some data set. And this is exactly, this trivially obeys all the axioms that I introduced before. So this one makes sense, which is why logistic regression is such a popular model in finance, of course, because this we can understand without having to think too much. And it also has all these reasonable properties. In this case, for example, I can take the expectation value to be the distribution of accepted population. So when I do attribution, I can see how different are you from the guys that got accepted, that got a loan. But yeah, the issue here is if I should stay true to my data or not. I mentioned, for example, that the dummy axiom is complicated when I have correlations in my data. So according to the Fair Credit Reporting Act, the customer has the right to know how they can improve their credit rating. What if I buy a house? Will my credit rating improve? If in my model I have owning house with weight 0, and I have real estate debt bigger than 1 million SEK, that gives me weight 1. So if I am true with the data, I know that these variables are correlated, but just asking the customer if they should buy a house, if that would improve your credit rating, if I was true to my model, I could say no. But if I were true to my data, I would say yes. So that's a conceptual difficulty here. That should we be true to the data, or should we be true to the model? And if we introduce causality, for example, that I try to model exactly how to change features and how they correlate, it becomes extremely complicated. So this is another issue that is not fully settled yet. But let's compare the attributions I get when I handle correlations and when I don't. And I just did a scatter plot for that, and you can see that it varies differently. On the x-axis, I have Shapley values or Shap values with correlations, so taking care of correlations with my features. And on the y-axis, I have it without my correlations. So a lot of variables that have 0 attribution in the one without correlation actually get attributions with the one that takes care of correlations. So the picture is completely different in these two cases. But as I said before, if I want to take care of correlations in my data, I break the dummy axiom, for example, and all my uniqueness properties of attributions break down as well. So it's not easy. Let's do neural networks, because that's what we all are so excited about nowadays, right? We're not happy until we can do neural networks. So in my case, I'm doing transaction modeling. So I have, in financial applications, I have 4 transactions. Transaction 1 for one customer. This is one of my this is a sequence in my training set, or validation set, or whatever. The first one was paid, so that's actually the customer paid that debt it had. The credit card withdrawal went through, whatever. And the second one was problematic. The one that wanted the money didn't get the money for some reason. The third one was paid, and I'm looking at transaction 4. Is this going to be paid or not? We can do this as a sequence labeling. I take the sequence and I label it, will the last transaction be paid or not? And that's exactly what the title comes from, sequence labeling neural networks. Here is what I'm trying to do. I have this series of transactions. So how can we model that with a state-of-the-art neural network? Yes, we can actually do that with self-attention. So that's from NLP, but we can readily apply it for whatever sequence problem we have. So let's say I have my 4 transactions, x1, x2, x3, and x4. I feed it into a self-attention module, and I have some hidden layer and a prediction layer, and I get my prediction for my y4 out here. I can say that to the bank, this is awesome. You should use this method for predicting all your credit risks. And they would probably say, nah, it's a black box model. No one can understand it. So that's why these axiomatic models come in. So just, if you don't know self-attention, it's from this Attention is All You Need paper, which is the basic for BERT and Transformer, which I think we've heard a lot about these 2 days. And attention is just the scalar product of my historic features. Yeah. In our case, K and V are the feature vectors for all our transactions, and Q is the last transaction. So you take basically your last transaction and project it out onto all the other transactions you had in the past, and you multiply that weighted sum with all the features that you get, and you get some linear combination that is basically incorporating the transaction history. So the intention of this module is to which of all the previous transactions are most relevant for determining the risk of the current transaction. Right? So this is my model, and now I want to apply these axiomatic attribution models to that. And this is also a funny slide. So what actually is shown by game theory or cost allocation research is that a lot of these axiomatic methods are given by path integrals. And that's also why what some guys from Google introduced, I think, 2017, to apply these methods to neural networks. In the game theory literature, this one is called Shapley, but by the Google guys, they called it integrated gradients instead. And that's implemented by the Facebook package Capdo. And we don't want to actually calculate the integral, so we need to approximate it, and we take this sum over points on the path down here, and actually the path method requires that I take a baseline, that I measure some point in my space that I choose, compare all the data points to, and then I take the path along from that baseline point to the data point that I want to calculate my attributions for. And this choice of baseline is clear in some applications, like in object detection, they take the black image. But in credit risk, it's not clear what baseline point you should choose. So then you instead take the expectation values of some data set, all the points in your data set. Let's take the accepted population again, the ones that got loan. So I end up with an expectation value over an approximation of my integral. And that's actually what's called expected gradients by Lundberg in 2019, and it's implemented in the Shap package in Python. So we can just plug and play here. And we get a picture like this out in the end. I have taken my model, my self-attention-based sequence labeling model, and do this, it's a PyTorch model. I put it into the Python package for expected gradients, and I get these attributions out for my transaction histories of my customers that are applying for loan. And it's a little bit hard to see probably, but it makes more attention to recent transactions. So transactions that are more recent in history get more attribution. And then attributes different values to different features that I have. Really small text probably. But I can look at, for example, my transaction histories that were paid, how the attributions are relevant for those. And the most important feature here is someone called feature 1. Otherwise, it's the time of the transaction, for example. Because we are doing self-attention, we have to code time in trigonometric functions, like in these self-attention papers. And if I look at transactions that were unpaid, I have a variable that says, are historic transactions paid or not? And for the unpaid transaction, of course, it pays a lot of attention attributions to the transactions in your history that were not paid. So it seems to make sense. And hopefully I can convince the financial authorities that this makes sense as well. I can do another plot of this, a heat map, because attributions in this context becomes a heat map, because when you have the features on the x-axis and the transactions on your y-axis, and it places attributions to if the most recent transaction was paid or not, and then it has a lot of attention on how long you have been customer. That is basically the age of your oldest transaction. So if you have been a customer for a long time, probably is lower risk. So it seems to make sense. Right. I also have a slide with some references if you want to learn more about this. As I said, it's a field that is happening a lot in right now, and I think you definitely should think about how you explain your models. because just plugging in a random explainability package, you probably get attributions that don't make sense because of these not conforming to the axioms that I have been talking about. So, and I think it's not really yet clear exactly which one you should use, but these integrated gradients, they make sense to me right now. So discussion about expected gradients, this paper, Shapley values in finance in these posts here. Right, that's me. Thank you.